Today, you are going to hear a little bit more about the Xradia Ultra X-ray microscope and how it can be used in various workflows, including in correlative workflows with transmission electron microscopy. Today, I had with me my colleague Mohsen. Mohsen is based in Germany, and he is our European application specialist for X-ray microscopy technology. Just before we start, a final reminder: for any questions, please do pop them in the chat and we will answer them at the end of the session. So with no further ado, I will hand over to Mohsen to take you through the Xradia Ultra. So thank you very much, Mohsen.
Thank you very much, Andy. Hello, everyone. So I'm happy today to present actually some capabilities of our Ultra X-ray microscope, and with a focus how it can be implemented in correlative workflows that are leading to targeted TEM sample preparation. So as a short introduction here, so about the portfolio of X-ray microscopy which is being offered by Zeiss. So that's the portfolio here. So with the focus on X-ray micro CT systems and actually the X-ray microscopy systems. So on the left side, you are seeing mostly the systems based on geometrical magnification, the categories that are having the focus on geomag-based systems, absorption contrast, and then diffraction contrast tomography as well. On the right side, actually, you're seeing the Versa family, which is based on dual stage magnification architecture. We will have a quick look on that. And then actually the Ultra family, which is involved in having optics for X-rays. All the X-ray devices are sitting on a, let's say, platform that is suitable for synchrotron, which means that the synchrotron quality let's say scans are guaranteed, and then the systems are upgradable. So for example, if someone goes for a context, so it can be upgraded all to the Versa family. And the Ultra family is totally different in terms of architecture, having optics for X-ray, that we will have a look. A short introduction on the background of the CT. So on geomag-based systems, so the sample finds itself between the source and detector, rotates itself. So the projections are being gathered, and then after that, a reconstruction step. And then as the 3D volume in a non-destructive way is available, so it is possible to perform virtual slices to have a look to the inside of the structure in a non-destructive way from any, let's say, angle, which is in fact aimed. And then as the data is available in a, let's say, as a 3D volume, it's possible to perform some quantitative analysis as well, like segmentation, volume of pores, volume of precipitates, and so on. So what is, however, the limitation of micro CT? So larger samples in case is, let's say, to be investigated. So for a higher resolution, one should take the sample as close as possible to the source, which is the case here. But the limitation of the geomag is becoming clear here as, for example, if the region of interest lies in the center of the sample, then it's not possible to get closer to the source to have the maximum geometrical magnification, and that's why the sample should be sacrificed to the region of interest. And then, like that, the high resolution is being achieved in the geomag-based systems. However, in the Versa family, so it's possible to have dual stage magnification, which means that the geometrical magnification is being combined with optical magnification after a scintillation step, which means converting X-rays to the visible light with a really high quality, and like that, the high resolution will be maintained across the high range of sample dimensions. So talking about numbers here in terms of maintaining the resolution at a distance. So looking to this graph, so the left axis is the resolution, and the axis here below is the working distance to the source. As you see here, for tiny samples, it is possible to achieve high resolution using for tiny samples in both systems, geomag-based and dual stage systems. However, once the samples get larger, or if you are intending to perform in situ experiments, you have to get away from the source, and this means larger distance to the source, and that's the region where the dual stage magnification shows its importance. And as you see, the resolution is being maintained in a system based on optics, while it is actually deteriorates heavily on geomag-based systems. So as a, let's say, conclusion just for VERSA systems, because the focus will be on the ultra one, the dual stage magnification allows us here to perform overview scans, let's say scout, and then to zoom in to region of interest while maintaining the resolution and without sacrificing the sample. It makes it possible, in addition, to generate additional contrast mechanisms that are missing in geomag-based systems like diffraction contrast tomography. So in general, the device is maintaining the resolution at a distance for large samples as well, and then offering optimized absorption contrast tomography, laboratory diffraction contrast tomography, propagation phase contrast, as well as, and additionally, high resolution in situ experiments are possible. The focus of today's talk will be, in fact, on the Ultra family. The Ultra family is, in principle, based on the architecture of having an optics for X-ray. So, in fact, we are using here quasi-monochromatic X-ray beam, which means, in principle, so having K-alpha 1 and K-alpha 2 lines in the X-ray pattern. So either from chromium K-alpha, so chromium source, which means chromium K-alpha 1 by 5.4 kilo electron volt, or copper, which is 8.0. So depending on the material, we will go for the for actually one of these two energies that will be discussed in the next slide. The device is offering, in fact, two image modalities: one, large field of view with a spatial resolution down to 150 nanometer, and one high resolution with a spatial resolution down to 50 nanometer. Speaking of voxel, a voxel size of 16 nanometer is possible in this instrument. So in principle, you have the X-ray source, quasi-monochromatic. So on the left side, a capillary condenser is available for focusing the X-rays on the X-ray photons on the sample, then a zone plate, a phase ring, and then, in fact, two image modalities, which means coupled scintillator and optical lenses, and then at the end, a detector that offers two image modalities. So comparison with the synchrotron qualities as the devices are coming from, let's say, synchrotron environment. So the Siemens star as a standard resolution sample, the left side has been done using the same device as SSRL synchrotron facility, and the right one is the same scan that has been done in the laboratory using a lab-based source. So as you see here in synchrotron, it's possible to resolve the 30 nanometer distance, which is the distance between the lines in the inner area of the standard specimen. However, no, 30 nanometer is not possible. Perhaps 50 nanometer is possible, which is a nice value as a lab-based instrument. So talking a bit about the available sources and energies, as I said, chromium K-alpha line offers 5.4, and copper K-alpha offers actually 8.0 kilo electron volts. So depending on the type of the material, so let's say from middle to low-Z material, it is recommended to go for the chromium source due to a lower energy because of having a nicer contrast. So as you see, for low-Z materials, so even if we go for a high, let's say, energy source, the absorption will be limited across the sample. So that's why we have to wait longer to compensate for the noise, while with the lower energy source, so there will be a nice delta in terms of absorption of X-ray photons, which leads to a better image quality and a nice contrast. On the other hand, having a higher density material, so in principle, it is recommended to go for the source with the higher energy, so that at the end, there is a good combination of signal to noise ratio, as well as actually the contrast in the image. So the Ultra device is delivering absorption contrast in one side. It is also possible to add optionally the Zernike phase contrast, which is based on refraction and makes it possible to visualize the interfaces much better. An example of which is being shown here. So you see here in this image on the right side, the absorption contrast tomography results, while the Zernike phase contrast results reveals in a better way the interfaces and the features inside the material. So trying to actually have to just show how ultra dataset would look like, that is in fact a prepared sample, a piece of the electrolyte containing anode, cathode, and electrolyte from the fuel cell. First of all, we are having a look to it using the, in principle, the large field of view, and then zooming in using the high resolution detector to have the spatial resolution of 50 nanometer. So this is just to show which type of data is being delivered using the ultra. In this case, we will have a look in an explicit slide here. On this example, the goal was, for example, in the first step, to identify pores and cracks within the electrolytes, and in the next step that we will have a look to go further in terms of analysis. So for your information, ultra is also capable of having in situ instruments and also in situ investigations while imaging it either in 2D and 3D. Imaging in 2D can be also be a sort of a live 2D imaging while, for example, compressing the sample or pulling the sample, and then in 3D is in fact a static in situ experiment. So which means that you're performing your tomography in certain steps. That's the ultra low stage designed for this microscope, which is actually capable of delivering two ranges of forces to the material, depending on actually hard or soft. You can go for a version that offers actually 9 Newton on that tiny sample, or a version which is having 0.8 Newton forces on that sample. What is possible here? Compression is possible, tensile, and also indentation. And then, as an example here, we are having a look to a live 2D compression examples of explosive crystals. The motivation behind this one was that the way that the explosive crystals are being cracked is having a influence on the way that these materials should be stored, and that's why understanding the cracking behavior of this material was really important here. And having the ultra low stage and imaging them while pressing them in compression mode helped a lot understanding the nature of this material. That's also another example of using, in principle, indentation and then perhaps 3D characterization to see how the cracks are propagating in dentine. So in principle, the yellow segmented feature here are cracks that are suddenly growing and in fact actually exploding, and then you can just see in which step so it is going to happen, and then you're having a full 3D characterization of your material with a resolution down to 50 nanometer. Another nice example is in fact tensile experiment on a single fiber of boron carbide or boron nitride. So that are being in fact used as building blocks or components of high performance, let's say, material that are being used in aircrafts. So in principle, in this study, the researchers wanted to understand, in fact, the exact mechanical properties of the bulk material. And for that, they indeed started from its building blocks. So that's why they have, in principle, they have taken an individual boron carbide fiber here in this case. So they just flip notched it for example, crack initiation, and they just pulled it using ultra low stage inside ultra X-ray microscope, and then just watched it in 3D to see how the failure is growing and propagating here in this individual example. The same can be done, for example, in compression on a shale rock, because understanding the cracking and fraction mechanism of shale rock will help later for deciding about the way that a drilling for fracking actually process should be decided. So this is bring an idea, for example, if the cracks are having a sort of a intragranular or intergranular growth, and then, for example, in this specific case, it was observed that unlike actually the expectations, the cracks are propagating along the grain boundaries, and that will help understand the cracking mechanism and the fracking mechanisms later to decide which way or which parameters should be selected later for drilling of the shale rock. So a heating stage is also available for the ultra, which means it's possible to just heat up the samples using this stage up to 500 degrees C from room temperature indeed, while we are observing them either in 2D in a live way, or for example, performing some steps and some breaks for 3D scans. As an example of that is the zinc powder particles, and then we just started to heat them in room temperature up to certain hours. We watched them in 2D, and then we performed a scan in 3D, and we just this helped a lot in actually selecting a time which the nanoparticles, or let's say which the nanowires are perfectly formed, and then one could see in which temperature and which times they are formed, and then later it is possible to perform a full 3D scan, perhaps once the sample is cooled down, to have the 3D information on that, or even actually at higher temperatures if the sample is stable enough. So now a cool message here, why, for example, ultra can be used in principle as a good complement for TEM investigations, or in another way, ultra can be used for a targeted TEM lamella preparation. So a key factor here is ultra is offering a nice combination of characterization volume and a resolution. So in fact, this combination allows to have access to a large volume, which is somehow reflecting more natural properties of the material without having too much dominancy of surface effect compared to scanning electron microscopes or electron microscopes. I mean, compared to the pillars or nanopillars that are prepared for the electron microscopy investigations. So if you have a look here, so for example, sometimes the size of the nanopillars for high resolution TEM investigations are getting down to 200 nanometer. Perhaps if atomistic resolution is needed, of course, that's the size of the pillar, because other than that, it's not possible to achieve to the high resolution TEM images if the pillars are larger than a certain level. However, one should accept that we should then live with the limitation of having the dominancy of surface effects on such a tiny nanopillar. But having looked to the dimension of, let's say, pillars for the ultra, we will see that we are talking about not in nanometer ranges, and rather than, for example, 50, 60, 80 micrometer, depending on the material, which is important because in these sizes, the surface effects are less dominant and the material is reflecting more or less actually the closer behavior to the bulk. So another example of use cases, besides having a larger volume and let's say and a good combination of resolution, is this fuel cell that we had a look shortly in some slides before. That is the high resolution ultra scan that is showing the LSM cathode, the yttrium stabilized zirconia anode, and then in fact the electrolyte in between. So in a first step, it's really nice to have the characterization of pores and also prolonged cracks in the electrolyte, because they are deteriorating, in fact, the performance of the fuel cell by letting the gas actually in to just transfer from one side to the other one. So in the first step, it's possible to investigate them, which is really nice, because if we want to go to investigate it using a TEM lamella, that's almost the width of a TEM lamella, which is being normally prepared, but perhaps really thin in the other dimension, which means that if we want to have a look to the same width using a TEM lamella, we are in principle seeing just that thickness. So that's the width, but the volume is not covered, and we are in principle seeing this thickness. So the probability that actually our TEM lamella is sitting in a nice or in a right region is really less. So this means that we are not having access to the volume, which is reflecting somehow at least a good statistics for our purpose that I will explain here now. So as you see here, the question will be, yeah, well, for further investigations, in case I would like to see the nature of this interface or wherever in my electrolyte using the high resolution of TEM. So the first question will be where I should place my TEM lamella. Indeed, the large volume of ultra, let's say scan results, will help using the workflows that will be presented later to navigate your TM lamella to the right region of interest. Imagine you just start for this void or for these cracks. You can easily take your ultra dataset now to your crossbeam laser width. You place your, let's say, that plane of interest for lamella with coordinates. Let's say you introduce it after registration to your crossbeam laser, and you get your lamella exactly right where you want to have it. And that's a huge help, because once you try to prepare the TM lamella without having virtual information over the volume, it's impossible, because you just simply from the surface that you are seeing under crossbeam. But here, having calibrated this data set with your crossbeam, later you will see it's possible to say to a machine that, please just get a TM lamella out of this area for me. That is actually very easy workflow. Beside that, Ultra is delivering kind of data or information which is simply missing, and it's not possible to get from any other method. Like, for example, the amount of triple phase boundaries that are being shown here in yellow. The reason for that is that the resolution of CT systems are not enough. Light microscopes, electron microscopes, and even TM are offering sufficient resolution, but since they are actually 2D methods, so you are seeing a cross-section or a projection of this area, which makes it impossible to have access to the lengths of triple phase boundaries. And why triple phase boundaries are important? Because that's the region in which electrochemical reaction in this specific case happens. And this means that in case we are having access to the lengths of these triple phase boundaries, we can be this can be used somehow as an input for our simulation model that reflects or simulates the performance of the fuel cell. So this type of information, as I said, so needs a good combination of volume, which means 3D information, and a high resolution, which is the case for Ultra with 50 nanometer spatial resolution. And like that, instead of having a projection, perhaps high resolution with electron microscopes, it's possible to have access to the lengths of triple phase boundaries and use it later as an input for the model. Another example of having Ultra answering properly the research question can be seen also from this publication. So in this publication, Drew et al. Tried to actually understand the mechanical properties of dentine as a function of tubule orientation, which is written here. So they just, what I'm actually showing here, including the Ultra data set, is also from their publication. What they have done here was using normal photography device, using light microscopes, electron microscopes down to TEM. And then at some point you see projections of tubules. However, you cannot really correlate them to the mechanical properties because, for example, in this light microscopy image or in that electron microscopy image, you see roughly the projections of the, let's say, orientation of tubules in 2D. In high resolution TEM images, you might see the nature of, let's say, interface between tubule and the matrix. However, the question is not answered, which is how these direction, the orientation of actual tubules correlate to the mechanical properties. As a next step, they just have got the Ultra with Ultra loaded stage. They just visualized the tubules in 3D while indenting the sample with this Ultra loaded stage. As you see here, different loaded stages. And the result is clear because, as was mentioned in the abstract as the goal for this study, it is possible now to have access to the mechanical properties, loading care, even the crack propagation. These are the cracks that are segmented within the dentine and then correlate them to the tubule orientation in 3D. So as an example about the workflow, how we can direct actually ourselves to the region of interest, to the right region of interest for a TEM lamella preparation. TEM lamella preparation is really important because TEM investigations are really time-consuming as well as expensive. However, the sample preparation to step is really challenging because that's the most important step. We would like to have a region of interest included in the TEM lamella. On the other hand, we are having a big limitation, which means that in the FIPSEM that is being normally used for TEM lamella preparation, we are just deciding from the surface, and then we cut through, and then with the hope that the feature is also staying there underneath the surface, and we are having it. However, with the workflow of using Versa machine, the dual stage magnification, to have the overview of the sample in 3D, and then taking it to crossbeam laser flip as an example to just generate a micropillar for high-resolution ultra investigations, can be used later to take again the sample after investigations using ultra 810 back to the crossbeam laser to have a look virtually without cutting the sample further, and then to decide and judge for a right place as a region of interest for the TEM lamella. So as an example here, so we are just staying with silicon plus graphite here. So anodes here. So a bit background of why this material. Energy materials are of focus today. So silicon particles, however, are known to actually increase extremely the capacity of the batteries. However, their dilation effect is, or let's say, they are deteriorating quite quickly due to cycling of the battery. So that's why it's really important to understand what is the mechanism of this deterioration, why the capacity drops so quickly in batteries that are being manufactured using silicon-containing graphite anodes. So as part of actually that investigation, so imagine now we would like to locate a TEM lamella to the right place of the anode, which is containing silicon particles. So finding it is a challenge because we want to just judge from the surface. So that's why we are just taking the sample to the Versa and performing the Versa scan. We are having access to a 3D volume of graphite anode, seeing silicon particles. And then based on this data, we can decide for a micropillar for the Ultra 810 machine that at the end provides us a 3D volume, a virtual 3D volume with a higher resolution of 50 nanometer compared to Versa. For the micropillar preparation, so in principle, we take the sample after Versa scans to the crossbeam laser. We are having a Atlas 5 software package. So it's a software for the connected microscopy that in fact is being installed on the crossbeam laser, and at the same time operates it and can also read and import all data sets from different kinds of microscopes that are being produced by ZEISS. And like that, you can just correlate many types of data sets together. What is being done here is now we are sitting actually in the crossbeam machine. That's the interface of the Atlas 5 software package. For the correlation, as a first step, we are importing the 3D X-ray microscopy data set, and we are visualizing just the surface of that as green, and we are having the surface of the battery inside electron microscope as gray. And the two surfaces can be calibrated using 3 points, and that's why we are just for the moment focusing on the surface visualization. And after calibration, as the two surfaces are calibrated, the volume is also calibrated, and the volume is being offered inside the flip machine now virtually using Versa X-ray microscopy dataset, which helps to navigate to the right region of interest after registration for the ultra micropillar. So what is being done now here is we have registered the images, so the cross-beam laser knows now the coordinates actually underneath the surface on the basis of the data available from Versa X-ray microscope. And based on those data, the laser, the cross-beam laser, is cutting to the region of interest. And a short word about laser here, why we are using laser here. Ion beam is actually having good polishing, or let's say final cut properties, or let's say it can give a cut when the region of interest is close to the surface. However, if the region of interest is in depth of the material, we need a proper tool to just give a cut. And in this case, for information, a femtosecond laser is being used, which is indeed bringing almost no damage, or let's say heat affected zone, to the material due to really a short pulse of laser. And after that, we will just use the ion beam to final polish the sample surface, and like that we will have the pillar ready for the ultra investigation, which is containing graphite and also silicon as well. And like that, the sample can be taken as a next step to the ultra investigation. And here, for example, you will see the maximum resolution which is being provided using Versa in background, and then the large field of view scan using ultra, which is 150 nanometer spatial resolution. And it's even possible to go one step ahead using the ultra to offer better resolution down to 50 nanometer, or a voxel size of 16 nanometer. However, our goal is achieved here, so which means that we now have a nice region of interest containing anode and graphite that can be actually, that based on that, we can decide, for example, for a region of interest somewhere in the volume for a TEM lamella, which is actually a smaller portion of this volume, and then just taking back the samples towards the crossbeam laser, and in principle using the same workflow, but this time to prepare the TEM lamella for further investigations. So talking about ultra scans, so scan time is becoming, in fact, an issue. Sometimes if repeated examples like scans are needed, like in situ investigations. So therefore, there are some modules to increase, to reduce the scan time by factor of 10 that we will have a look now, while keeping the scan quality like original. There is also sometimes need to just increase the image quality. As the scan time is not a problem, for example, we can just devote the needed scan time, but in principle, we would like to take more out of the device, and in principle, visualize features that are normally are hard to visualize. And in those cases, in principle, we are increasing the scan quality using AI-based reconstruction techniques. So we have developed reconstruction algorithms based on artificial intelligence that are focusing more on the feature, and then using some algorithms that are actually developed by us here. And then, as I said, the goal will be either to increase the image quality or keeping the image quality while reducing the scan time up to factor 10. There are also many features in this advanced reconstruction toolbox that we just shortly have a look to them. So Deep Recon Pro, which is actually a reconstruction based on deep learning, will be used to accelerate the scans by factor 10 while keeping the quality, or even increasing the quality while keeping the scan time. Deep Scout is a nice region that is being used to, in principle, expand the high resolution of a higher objective over a large range or field of view of a lower number objective. So imagine you're using a 4x objective for the overview and 20x objective for the high resolution, and part of that field of view, you can use Deep Scout to have the full resolution across the overview based on AI. Phase Evolve is available to remove the phase artifact. Mars actually for multi-material artifact removal, for example, once you are having beam hardening due to having different densities beside each other, and optorecon, which is a technique to accelerate and improving the image quality based on iteration. For the moment, for today, we will just have a focus on Deep Recon Pro, and then actually few examples on Deep Scout. So that's an example of a composite materials, fiber reinforced, full quality 3000 projections, and then that took almost 9 hours to visualize. Fibers are perfectly visible, no quality issues. However, in case, for example, the time is an issue due to in situ experiments, we need to reduce the scan time dramatically in case time is an issue for us. Now we are having to virtual 2D cuts and exports of those slides here. So as you see, by having the full 3000 projections, we are having a nice 2D export, virtual 2D export, but it will take 9 hours to have those results. A way to reduce the scan time is living with, in fact, a lower number of projections, which means in this case, cutting 90% of the projections. We use 300 projections for the reconstruction, perhaps using standard algorithms that are available. However, the scan time is lower, but the quality is not satisfactory. What Deep Recon does is, in principle, maintaining the original quality and even some improving it while having the scan time quite short. So as you see here, if you are planning, in principle, in situ experiments, if you have, for example, something like 9 stops, 10 stops for your in situ experiments that you need 3D tomography, instead of having 10 times now 9 hours, we will have one time 9 hours for the training, and then 9 times just, let's say 1 hour. And like that, we are done with the whole experiments in a much quicker way. In this case, instead of 100 hours, 19 hours, while keeping still the quality in the original level or even better. So an example of, let's say, increasing the image quality, that is the pouch cell, an example of a pouch cell in battery material investigation. And as you see here, if the region of interest is the cathode, it's not a big deal. It's possible to see it in a large pouch cell, a bit noisy, but you can live with this increasing and enhancing a bit contrast. But once the focus is the graphite anode, because the graphite is really low absorbing and always a challenge to produce contrast, it is really difficult to just even achieve high quality, or let's say acceptable quality, while having a large specimen, even in 24 hours. Deep Recon Pro, in principle, is simulating a scan which is longer virtually by, let's say, a factor of 10. So imagine like simulating a scan which is taking something like 200 hours to reach the same quality, but then you have it in your original scan time, but the features are actually resolved in with a better quality. So the same, in principle, some examples on Ultra. So the challenges that are associated with Ultra, let's say, scans. Ultra, as I said, so for example, was directly taken from synchrotron architecture and environment, but equipped with a lab source. So that's why the scan times can be a challenge. So, for example, we might need some hours already, 8 hours, 10 hours, 24 hours, sometimes for high resolution scans. Then there will be some challenges probably with the noise level and so on. And that's why advanced reconstruction toolbox will help here to just reduce the scan time while improving the image quality. As an example here, 1000 projections, for example, in this case took 18 hours. However, we will cutting, let's say, 75% of the projections, it's possible to have some results in 4.5 hours with the standard reconstruction, pretty much noisy. Using advanced reconstruction toolbox, you will see it is possible to have much better image quality while having shorter scan times here. Another example is actually from bin 1, 64 nanometer voxel size. So in principle, it is using the standard reconstruction here. You see here, it is possible to move from 15 hours to 2 hours, but we end up at the end with a noisy image. While using the Deep Recon Pro for the Ultra, we can improve the image quality while keeping the scan time constant. On the other hand, we can just decrease the scan time dramatically while keeping the quality. And please also compare the standard reconstruction using full number of projections with this one, which is actually the AI-based reconstruction, even 6 times faster. Even if, for example, in situ experiments are needed, or due to whatever the reason, we need to go for really short scan time, it is possible to get nice examples of having nice quality within just 16 minutes. So by binning to going, for example, a bit high with the resolution, which is 128 nanometer voxel size in this case, it is possible to perform a full tomography in 2 hours roughly, and then using the Deep Recon Pro to increase the quality, or using it to reduce the scan time 8 times faster, as you see here, and then what you have your result within 16 minutes. And if any sort of quasi dynamic in situ experiments are needed, so here it can be somehow useful. So 2 examples on Deep Scout before we come to the end. As I said, in Deep Scout, we are implementing the AI reconstruction technique and technology to expand the high resolution information over a larger field of view. What you are seeing here now is a composite material, perhaps with a, let's say, lower objective, covering a large region of interest. Perhaps it's always nice to have the resolution, the high resolution in some part of it, but if we are having it across the whole, it is in fact changing a lot the available statistics in terms of sample characterization. And this is what happens if we are using the AI to improve the resolution of a large field of view scan. And in principle, you are increasing and expanding it to 3D. You are increasing the high resolution volume by a factor of 125 in 3D, which is indeed a considerable number, delivering a high statistic and volumetric information while maintaining the resolution. So you can just compare these two now. Yeah, that's Deep Scout, which means resolution, which is recovered using a higher objective, but across the whole region. And you can just compare these 2 results here. Another example that can be observed here is from a, let's say, soybean sample. That's the large field of view scan. And then per mouse click, so you will see now the result from the Deep Scout, which is indeed extended high resolution over the whole volume using AI. And then in order to better identify the differences, so we just zoom in and have a look, please. That's the standard large field of view reconstruction. And that is, in fact, the recovered resolution after performing the Deep Scout. And this is also clearly visible here, the difference. So like that, I would like to end my presentation, and thank you very much for your attention.
Excellent. Thank you very much for that very in-depth talk, Mohsen. I really hope that everyone who attended today enjoyed that talk and managed to learn something a little bit more about the Ultra XRM technique.